It's a great example where if you tried to get y all by itself in this equation on one side without any y's on the other side, it would be very, very difficult. Because there's a y on this side and there's a y to the 7 on the other side. That being said, we can imagine that if that were possible, if we got y all by itself as something with x on the other side, then we could do the derivative of this and figure that out. So for this one, if we're going to find y prime, we're going to look through this whole equation and do the derivative of each thing separately. We have to notice that in this one, we have two functions multiplied by each other. X cubed is one function, and y is another function. And that y function has x in there somehow. So we could, because there is a relationship between x and y. So when we're doing y prime, we go through each thing. This to the derivative with respect to x here, no problem. That's just 12x cubed. A little bit of foreshadowing here. I'm going to move this over. 12x cubed minus bracket. Here we have the product rule. Okay? We can keep the second one the same, which would just be y, times the derivative of the first, 3x squared, plus keep the first one the same, which is x cubed. And what's the derivative of y? Just y prime or dy dx. Because it's just y. If you did the definition of the derivative, you would get y prime equals whatever that would be. So if we take a step backward, okay, this implicit differentiation is based on the simple idea, and this statement almost seems too simple to be true. The derivative of y is y prime. The derivative of y is dy dx. So when I need to do the product rule here, and at this point I need to do the derivative of y, I just write y prime. Equals, derivative of 15 would just be 0. And what's the derivative of y to the 7? It'll be a chain rule. I would bring the 7 out in front and subtract 1 from the exponent, and then say, what's the function inside? It's y. What's the derivative of y? Y prime. Now we wanted to find out what y prime is equal to. So we need to do algebra to get that by itself. Can you see right now that we have y prime here and here? If I can get all my terms that have a y prime on one side of my equation and everything else on the other side, then I'll be able to factor that y prime out to just get one of them and divide to solve. I should not have written this at the beginning. There we go. So make sure you erase that. Shouldn't have two equal signs there. So we took the derivative of everything in this equation. We got two y primes. We're going to just do some algebra. I have that negative outside the brackets here. I'm going to just distribute that. Distribute that negative. I'm going to move all my things with y prime. And I personally like using dy dx in this case because it really looks different. The y prime sometimes looks like a y to the 1, and it can get a little bit harder to see. But since this question used y prime, that's what we're using. I'm going to move the 3x squared y over to the other side and the 12x cubed over to the other side. And at this point, we can factor out the y prime. Here's our y prime, here's our y prime. Now they're both on the same side. And now we can factor that y prime out. And now if we know a point on our original relationship, we know the x-coordinate and the y-coordinate, then we could find the slope at that specific point, even though we can't solve and get y in terms of x as a single function. So even though we couldn't get an explicit equation, we can still find the derivative.